Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying Binomial lecture 5. So this is the last lecture of Binomial and we'll be talking about negative and fractional indices over here, and also we'll be talking about multinomial theorem. So let us start with the negative indices, and before starting let's build up certain series expansions to finally derive the formulas for negative indices and fractional indices. So S equals to 1 plus x square plus x cube plus x4 till infinity for mod x less than 1. We know that this is a GP and summation of GP is 1 upon 1 minus x. Now I'll try to write this in a different format. I'll write this as 1 minus x raised power minus 1. Similarly, if I try to write an AGP, that would be 1 plus 2x plus 3x square plus 4x cube till infinity, again modulus x less than 1. Now I can write this as 1 upon 1 minus x square. We actually derived it, that this comes out to be 1 upon 1 minus x whole square. Again, I can write this in the format 1 minus x raised power minus 2. So basically what I have done is I have tried to rewrite this expansion series in terms of this binomial series, but with a negative index. But a thought can come to my mind that this is possible only for few cases. This might be possible only for few cases, but might not be very generic. So let's try to derive a generic formula how to arrive at these particular expansion series for these kind of conditions. Okay, I'll again go back to 1 plus x raised power n. So that is c0 plus c1x plus c2x square plus c3x cube plus c4x4 till cn x raised power n, right? Now let's try to write this in a different format. C0 is nothing but NC0. So NC0 is nothing but 1. C1 is NC1. So that is NX. So C2 is n times n minus 1 divided by 2 factorial times x square plus C3 over here. C3 is n times n minus 1 times n minus 2 divided by 3 factorial multiplied by x cube and so on, right? So basically what I've done is I have written NC3 as this, NC2 as this, NC1 as this, and C0 as this one, right? Now this is our 1 plus x raised power n. Now what if I replace x with minus x over here? I'll be getting 1 minus x raised power n and replace n with minus 1. So I'll be getting 1 plus minus 1 times minus x plus this would become minus 1 times minus x whole square divided by 2 factorial, and this would become minus 1 minus 1 minus 1 and minus 1 minus 2 times minus x whole cube divided by 3 factorial and so on. So I'll be getting 1 and plus x over here, right? And plus this minus and this minus would become positive and this becomes 2. This gets cancelled out, so this becomes x square. Now we have 4 negative signs over here, 1 2 3 and 4 from here, so again it will become positive. And we have 3.2.1, so 3 factorial gets cancelled out, it becomes x cube. Now I can see that it's becoming this series only, right? 1 plus x square plus x cube plus x raised power 4 till n, nth term, because we have defined for n terms only. Now if I make that as infinity, in that case we can again reach towards infinity. So basically my understanding came that I can use the same formula but in a different format even for the negative indices, and that would also work. Similarly, I can extrapolate that the same formula would work again for the fraction indices rule, but we don't have to write in this format because we cannot define NCR for negative index. So basically I have to write this in factorial format and then use that factorial format for fractional values of n and or for negative values of n. That can make use. We cannot use this for the negative or fractional, but we can definitely use this one for the negative and fractional, and that would work, and we have checked that. You can also use the value of x equals to minus 2 or x equals to x square, then also it would work perfectly fine, right? But there is one problem over here. In this one we derived only for such a condition. So again, if we are using the negative index or the fractional index, we'll always have to consider mod x less than equals to 1. And mod x doesn't mean just the x value. Let's say if we have 1 minus 2x raised power, let's say minus 2 over here. In that case, in that case 2x mod should be less than 1. Doesn't mean just x. X means anything over here that should be modulus of that should be less than 1, right? So this condition has to be followed if you have to use this kind of expression for any kind of binomial expansion, right? Now let us generalize it for the fraction indices as well. So 1 plus x raised power n equals to 1 plus nx plus n times n minus 1 divided by 2 factorial x square plus n minus 1 n minus 2 x cube divided by 3 factorial till the infinity for mod x less than equals to 1. So this is the generic formula for both fractional as well as negative indices, right? And for positive, we already know that. Now let's try to find out a simpler form, simpler version for specifically negative indices, negative integral indices. So let us derive for 1 minus x raised power minus n, where n belongs to natural numbers. So basically this is a negative index and we have 1 minus x over here. It's not for 1 plus x raised power minus n. We are specifically deriving for 1 minus x raised power minus n, right? So if I try to write it in generic format, it would become 1 plus minus s, n minus x plus minus n minus n times minus n minus 1 divided by 2 factorial minus x whole square plus minus n minus 1 minus n minus 2 divided by 3 factorial minus x whole cube till the end. Now we'll be getting 1 plus nx plus n plus 1 by 2 factorial x square plus n plus 1 n plus 2 x cube divided by 3 factorial and so on, right? So basically I can write this as nc0 plus I can write this as nc1 plus I can write this as n plus 1 c2, this is x over here, this is x square over here, right? Plus this is n plus 2 c3 x cube till the end, right? So basically I can generalize it. If we have the second term, basically if we have 2 power basically x square over here, then we have the 1 minus term over here n plus 1. If we have 3 over here in the power, then we have n plus 2 over here, n plus 2 c3. So the general term shows that if they want to ask you coefficient of x raised power n, then that would be n plus n minus 1 cn. So this is how you have to take the generalization for only this kind of case, 1 minus x raised power minus n, where n belongs to natural numbers, right? Now let us talk about binomial approximation. So again, we'll start with 1 plus x raised power n equals to 1 plus nx plus n minus 1 by 2 factorial x square plus n minus 1 n minus 2 divided by 3 factorial x cube till the end, right? Now let's take x equals to 0.0001, and if I try to find out the value of x square, I'll be getting 0.000001, right? I can see that there is a very less significance of this number in the life of this number. If I add both of them, there is no significant change in this number, in the value of this number, right? So similar concept can be used over here. If x is tending to 0, in such a case, we can ignore the higher order numbers and we can just write this as 1 plus x raised power n equals to 1 plus nx. But this is only and only possible when x is tending to 0. X means anything over here. If it's written 1 plus 2x raised power n, that means 2x is tending to 0. It shouldn't be like that, okay, we just making x is tending to 0 and then we are done with the case. That's not the case over here. And also, one should be here. It shouldn't be like 2 plus x raised power n, then we can write it as 2 plus nx. It's not possible because we are defining it for 1 plus x only. In that case, we'll have to take 2 raised power n as common out of the bracket, and then we can use 1 plus x by 2 raised power n, and then we can use the binomial approximation. So you have to remember that this any term over here should be tending to 0, and over here it should be 1 only. Only in that case we can use this kind of approximation. Now let's look at one example. The coefficient of x raised power 100 in 5 minus 4x divided by 1 minus x whole square is. So basically we have to use the concept of 1 minus x raised power minus n in over here. How? So this would become 5 minus 4x times 1 minus x raised power minus 2. So this is how it becomes, right? So I can write it further as 5 times 1 minus x raised power minus 2 minus 4x times 1 minus x raised power minus 2. So basically we have to find out the coefficient of x raised power 100 over here, and we have to find out the coefficient of x raised power 99 over here, and then add them because we have x over here additional, right? So based on our generalization, we studied that if we want to find out the coefficient of x raised power 100, what we'll be getting, that would be n over here, that is 2 plus the one which has been asked, 100 minus 1 c 100, right? So this is the one multiplied by 5 minus 4 times x is already there. So the coefficient of x raised power 99 is minus 4 times 2 plus 99 minus 1 c 99. This is the one, right? Now this would become 5 times 101 c 100 minus 4 times 100 c 99. So this is nothing but 101 only. So 505 minus, and this is nothing but 100 only, 400. So this would give me 105 as the answer. D is the correct answer. Now let us talk about the multinomial theorem, and this is the last topic of today's lecture and of the binomial series. So let's start with the generalization. X raised power x plus y raised power n equals 2, and we'll write the general term. That would be NCR dot x raised power n minus r dot y raised power r. Right. Now I can further write it as n factorial divided by r factorial n minus r factorial multiplied by x raised power n minus r dot y raised power r. Now one thing I can see over here, whatever the power is over here, we have divided n factorial by that. Whatever the power over here, we have divided the n factorial by that factorial, right? So I can further write it as n factorial divided by, let's call it as r factorial, and let's call it as capital R factorial. So this would become x raised power capital R y raised power r. Or you can write it as a and b over here, and this would become a factorial and this would become b factorial, right? So this is how we can generalize it, right? Now we can use the same extrapolation for the general format of multinomial theorem. So let's say we have been asked for x plus y plus z raised power n, then we can use the same kind of generalization. What we'll be doing, we'll be writing n factorial divided by a factorial b factorial c factorial multiplied by x raised power a dot y raised power b dot c raised power z raised power c, right? And a plus b plus c equals to n, because over here it was n minus r plus r. So basically this power has been divided everywhere in terms. So over here we have 3 terms, so we have divided the power in 3 terms, a plus b plus c equals to n, and dividing the factorial of individual terms in the denominator, right? So this is our multinomial theorem, and that's the only thing we have to study in multinomial theorem, and then we can directly jump on to solving questions. So let's see one example. Find the coefficient of a raised power 5 dot b raised power 4 dot c raised power 7 in the expansion of bc plus ca plus ab raised power 8. So we have bc plus ca plus ab raised to power 8. Now we can write the general term as 8 factorial divided by, let's say I'm calling as x, y, z powers over here. So x raised power x factorial dot y factorial dot z factorial multiplied by bc raised power x dot ca raised power y dot ab raised power z, right? Now the first thing to understand is over here is x plus y plus z equals to 8. Now it's been given that the term over here is a raised power 5 dot b raised power 4 dot c raised power 7. So let's try to write in this kind of format. So basically we have b term over here and b term over here. So let's try to write that in the format, right? So this term would become b raised power x, and from here I'll be getting b raised power z. So basically I'll be getting x plus z. And similarly over here c raised power x is there, and we have c raised power y over here. So we'll be getting dot c raised power x plus y. And also we have a term over here and a term over here. A has y plus z. So a raised power y plus z. Now with the given condition, y plus z should be 5 and x plus z should be 4 and x plus y should be 7. Now what we can do, we can subtract all of them from here and find out the value of x, y and z. So z would come out to be 1, and from here x would come out to be 3 and y would come out to be 4, right? So the coefficient would be 8 factorial divided by 3 factorial, 4 factorial and 1 factorial. So this is the value of our coefficient. So today's lecture was till here only, and this marks the end of binomial series, and from tomorrow onwards we'll be starting with PNC. So let's meet tomorrow. Thanks for watching.